All right, welcome. In this video, I'm going to be doing some surface area examples for multivariable calculus. So this is where we've got a surface defined by z equals f of x and y, and we want to know the area of that surface, and we're going to find that using a double integral. So just to remind you of what we learned recently is that the surface area of a function f of x and y over a particular region R in the xy plane is going to equal the double integral over R of the square root of fx squared plus fy squared plus 1 dA. Okay. And that's going to be our formula that we're going to be working off of. And so I'll leave this up probably for the first one, and then we'll just keep using it, and well, you'll just know it. Okay, find the area of the surface defined by 13 plus x squared minus y squared that sits over the region defined by the circle centered at the origin, radius 2. Okay. So I'm going to draw my region. Okay, that's got radius 2. So I'm going to be wanting to integrate using polar coordinates. Will make my life much easier. So ZF, I just call it Z, equals 13 plus x squared minus y squared, okay, meaning that zx equals 2x and zy equals negative 2y. So the integral that I need to run is the double integral over region R of the square root of zx squared plus zy squared, well, that'll also be positive 4y squared, plus 1 dA. Okay. Now I need to convert to polar. Okay, so I know that my bounds of integration, theta is going to go from 0 to 2 pi because it's the whole circle. R is going to go from 0 out to 2. And 4x squared plus 4y squared, that's going to equal 4r squared. Okay, dA is r dr d theta. And all right, r is in the interval 0 to 2, and theta is in the interval 0 to 2 pi. Okay, so I'm going to be double integrating on, let's see, I'm going to actually do d theta dr because the integrand is only going to depend on r. So I'm going to do, actually, I'll do r and then theta on this one, and if there's another one where I can do that with, then I'll just use the calculator. Okay, so I'll show you how to do it by hand. This one, I'll do the calculator on the other one, if such another one pops up. I haven't forgot what's all on this problem set. Okay, so r is going from 0 to 2, theta going from 0 to 2 pi. This is the square root of 4r squared plus 1 r dr d theta. Okay. Now this is going to require some more room. Okay, have a few more integration steps. Okay, along the way, this is going to require u substitution because of that r squared inside the square root. We don't have an antiderivative for that. And I'm going to look over here and say, all right, I want u equals 4r squared plus 1. du is 8r dr. Okay, but I just have 1r dr. Okay, so I'll have an eighth of du. And then when r equals 0, u will equal 1. And when r equals 2, I'll have 17. Okay. So now I'm going to be integrating from 1 to 17. Theta is still going from 0 to 2 pi of the square root of u times an eighth of du, then d theta. So it's the square root of u. dr is 1/8 of du, and then d theta. Okay, I meant to change those to blue also, I just didn't. Okay, so I've made my u substitution. I'm ready to go. This is 2/3, and 2/3 u to the 3/2, this antiderivative. And I'm going to pull the 2/3 over here and Okay, yeah, I guess that's fine. Because we wouldn't be getting the square root of 17, or 17 to the 3 halves when I plugged in 2 for that. I was thinking it's supposed to work out better, but I don't think it is. 2/3. So 2 over 24 is going to be 1/12. So it's u to the 3 halves as u runs from 1 to 17. So that's 17 to the 3 halves minus 1 to the 3 halves, and we'll integrate that with respect to theta. Well, this is just a constant, so I'm going to factor that out as well. So this is 17 to the 3 halves minus 1 divided by 12 times the integral from 0 to 2 pi of d theta. Okay, that's just going to be theta as theta runs from 0 to 2 pi, so it's going to be 2 pi multiplied by this. So I've got in total 17 to the 3 halves minus 1 times 2 pi would be times pi and divided by 6. Okay, and that's going to be my surface area. The second one, find the area of the surface defined by z equals, this is one we're going to be able to do by hand. Okay, 3 plus x to the 3 halves. I recognize this one from AP Calculus. Okay, and zy is going to be 0, so it's going to be just fine. All right, I've got over, what kind of region? Since over the rectangle with vertices at the I better just draw this. It's going to be too much to keep track of. The origin, 0, 0 and 4, 3, 0, and 3, 4. Okay, and that's the region I'm integrating over. So I know that zx is going to equal 3 halves x to the 1 half. Zy is going to equal 0. So the integral I'm interested in running is the double integral over region R of the square root of zx squared. So that would be 9/4 of x to the first plus 1. Okay, plus 0 squared plus 1, but dA. Okay. Now, it doesn't matter what order I go in. I would maybe, man, I'm telling you, it doesn't matter at all because it's a rectangle. So I'm going to just say, all right, let's do dx and then dy. Let's knock out the antiderivative step first, and then the second step will be easy. Okay, so y is running from 0 to 4. X is running from 0 to 3, and all 4 of these are constants because this is a rectangle. Okay. So I'm going to do dx and then dy. Okay, now I know this is 9/4 x plus 1 to the 1/2 power, so I'm going to, and this is just a linear inside, so I'm going to be able to just kind of cook up an antiderivative for this. So this is going to be 9/4 x plus 1 to the 3 halves. I would multiply by 2/3, but I think what I'm going to do is say, all right, if I took the derivative of this, I'd have 3 halves of this thing to the 1/2 times 9/4. So I'd have 3 halves times 9/4 out here. So that's, what would that be, 27 over 8. And I don't have 27 over 8, so I'm going to prepare for that by multiplying by 8 over 27. This is also what I would get if I did 2/3 and then divided by 9/4 or multiplied by 4/9, however you want to look at it. Either way, that's going to be my antiderivative as x runs from 0 up to 3, and we're still integrating this with respect to y as y runs from 0 to 4. All right. Okay, we can do this. And then, because this is just going to be a number, and we're going to factor the whole thing out. It's going to be all right. So I'm going to have, let's see, what am I going to be having here? Oh, plug in 3. 9/4 of x, that's 27 over 4 plus another 4 over 4 is 31 over 4. Okay. Okay, and then when I plug in 0, that is not going to be 0. Okay, I almost glad I caught myself on that. It's a very typical AP Calculus mistake, right? To assume that since the lower bound is 0, it's not going to contribute anything. Okay, so it's 8/27 of this minus, when x is 0, that's 1 to the 3 halves. Okay, but that's what I would get, and I'm still integrating that from 0 to 4. So since this is just a constant, I factor that out, integrate from 0 to 4 on dy, and that is going to be 4. So that's 32 over 27 times 31 over 4 to the 3 halves minus 1. Okay, that's a number. All right. Number 3, find the area of the surface defined by I'm not sure I like the look of this one, but over the region where f is between 0 and 1. Okay. Okay, so we're going to have to do some work to figure out this region. Okay, the square root of x squared plus y squared, that is going to make, well, it's definitely going to have, circular cross sections. Let me think about this for a second. It's like on one hand, I think it's, no. Oh, it's a cone. Okay, so it starts at the origin and it goes up, and the cross sections are circular. Okay, so that makes a cone. So we're interested in the surface area that's between. Okay, well, I can see that where f equals 0 is only at the origin, and then where f equals 1. Let's just do a little bit of investigation here. Okay, 1 equals the square root of x squared plus y squared. So I can maybe square both sides and say 1 equals x squared plus y squared. And we know what that is. That's the unit circle. Okay, so I know I'm running from the origin out to the unit circle. So that's going to be that region right there that I'm going to be integrating over. And so it's just the unit circle again. So I'm going to need to use polar. But that's probably not a surprise because of that. And that will actually be really helpful because that's the square root of r squared. Yeah, I like where this is going. All right. So I'm going to say the surface area. I'm going to have to, I'm trying to think. Is there, I'm not sure. You know, if you're thinking, wait, could I convert to polar and then take the surface area that way? You should investigate that on your own. I'm not 100% sure that that's a valid technique. Consequences of changing that all over. So I'm going to set up the surface area integral the old way. And well, I think that'll be all right too. All right, so fx is equal to 1/2 of x squared plus y squared to the negative 1/2 multiplied by the derivative of the inside with respect to x, which is 2x. Oh boy, that doesn't look great. But I think we'll be able to, do something with this. And then fy is going to be very similar, except when I multiply by the derivative of the inside with respect to y, it's going to be 2y. Okay, not sure where this is headed. Let's just set up the double integral though. Okay, this is the double integral over r, which is the unit circle, of the square root of fx squared. Now if I square this, I'm going to get, first I'm going to do that, right? I'm going to have x squared in the numerator, and well, I had the square root of x squared plus y squared in the denominator, but I just squared it, so I'm just going to have x squared plus y squared. I think this is going to convert to polar and be pretty nice, but I'm not sure how that's going to play out. Oh, yeah. Look at that. That's just 1. Is that supposed to happen? Okay, well, I'm just going to have faith. Okay, man. Right, because, yeah, we're going to combine these with common denominator. I'm going to have x squared plus y squared over x squared plus y squared, and that's 1. And so I'm taking the square root of 1, and I'm just getting 1. And how is that possible? This is basically saying that the area of the cone is the same as the area of the circle. I'm not sure what's happened here. Maybe I've made an error, or maybe there's some sort of like geometric reality that I'm not seeing here when you you know, take the unit circle and you fold it up to become a cube? I don't know. Anyway, I'm sure there's some sort of topological description of what's going on there. What I'm going to say is that the double integral of r over r of dA is just the area of r, and I know how to find the area of r. It's pi r squared. The radius is 1, so that's just going to be pi. Okay, really not sure about this one. Okay, I'm not sure, but I'm just looking at what I did. I don't see any errors, so that was a weird one. But, you know, sometimes you get a weird one. Number 4. Area of the portion of the plane that sits in the first octant. Gladly. Okay, after that one. So this is going to be nice and rectangular. 24 minus 3x minus 2y. Okay, so I know this is going to be one that has positive x and y and z intercepts. So I'm going to just kind of draw that. Okay, z is 24, whereas x is going to be 8. And y would be 12 at the intersection. And I don't think I've drawn this to scale at all. But that's okay. Okay, so we're looking for the surface area of the surface that I'm shading on. Okay, and we'll be able to do that. Okay, we need to first write down the region we're integrating over. Okay, this is intercepting at 12 and 8. Okay, so negative 12 over 8 is negative 1.5. Okay, so this line has slope negative 1.5, and so I'm going to say, all right, I am going to set up for the order dy and then dx because I just want y to run from y equals 0 up to y equals, what was it, 12 minus 1.5x. And then when x is equal to 8, 8 times 1.5 is the 12, and I get y equals 0. Okay. And then x is going to run from 0 to 8. So I'm going to integrate the double integral as y runs from 0 to 12 minus 1.5x. X goes from 0 to 8. Okay, I'm going to need my square root, but these partial derivatives are going to be really easy to take. So it's going to be the square root of zx squared would be the negative 3 squared, plus zy squared would be positive 4, and 1. Okay. Now, I'm going to, again, now I may have made a mistake. I probably got ahead of myself doing that work, because I see this as a constant. I'm going to factor it out. Okay, square root of 14 times the double integral over r of dA. Well, the double integral over r of dA, I'll just kind of underline that in blue, that represents the area of that region right there. And I could find that using geometry, right? So I'm going to say that that's the square root of 14 times 1/2 times the base times the height. Okay, so that would be, I think, 48 root 14. I like that one a lot better. All right, 2 more. Find the area of the surface defined by G, which is 2x plus y squared that sits over a triangle. Could be exciting. A little worried about the antiderivative step, but we'll see. Okay. Y equals 2x plus y squared. That sits over the triangle with vertices. I'm going to have to draw this at the origin, 2, 0, and 2, 2. All right. Oh, okay, I think because this is linear and its partial with respect to x is going to be just 2, we're going to be able to run this antiderivative. The one that I'm really concerned about is the one that you can't switch to polar, and it's like, say, x to the third plus y to the third. I think that the integration steps in that is going to be really unpleasant and, you know, maybe not something that we're able to do. Okay, but looks like I may have avoided that. Just got to make it through this one and the next one. I did not vet these problems before I put them on the problem set, I'll tell you that. Just found some surface area problems and threw them on. All right, so gx is 2, gy is 2y. So I'm interested in double integrating the square root of 4 plus 4y squared plus 1 dA. Yeah, 4y squared plus 5 is going to be, well, yes, we can use the calculator trick. I'm not sure how they were proposing to anti-differentiate this, because you can't do polar, you can't just get yourself a, well, I guess you could do polar. You'd say this is the line x equals 2, that's r equals, I think, 2 secant theta. I don't think that's going to be the way to go, though. I think we're just going to use our calculator, and this will be a good example of when to do that. So we're going to need to decide on an integration order. And me personally, I would probably prefer dy and then dx, because I can find a formula y equals f of x a little quicker than I can find a formula for x equals some function of y. Okay, so we're going to have our first representative piece be right here. This is y equals 0. And if this is x equals 2 and this is y equals 2, well, that's got to be the line y equals x. So that wouldn't have been too hard to find an equation for x as a function of y, but this is not as natural to us. So y is running from 0 to x. X goes from 0 to 2. Okay, the square root of 5 plus 4y squared dy and then dx. Oh, but I'm realizing I just said I needed to do dx and then dy so I could use the calculator, right? Because I don't have an antiderivative for this. I will tell you, I'm pretty sure that one does exist. Let's see if I can flip back here to the table of integrals and track it down real quick. I think it would require a trig substitution, which is something I didn't show you how to do last year. All right, just give me a second. Forms involving the square root of u squared plus or minus a squared. Yeah, that's going to be it. Yes, here it is. Number 26. Yeah, there you go. The antiderivative of u squared plus a squared with respect to u would be all of that stuff, and we'll use a calculator. So I'm not going to give you that table of integrals when I give you a test. I'm just going to give you a calculator and just have you know what to do. So I'm going to have to reverse the order of integration. And that's actually probably good that I got one of those in this video. So I'm going to need to go dx and then dy. Okay, and x is going to run from, I'll just sketch my region. From left to right. Okay, so I start with x equals y. That was not a hard one to solve for. And then I end with x equals 2. So that'll be from y up to 2. And then y would run from 0 to 2. Oh, no, not red, blue, black. All right. Yeah, that 2 is going to be really troublesome. If it was just the 0 to y, then I could probably, I'd have been able to use the substitution on that, but that's not going to happen, so I'm going to have to use a calculator. So I'm going to let, anti-differentiate this with respect to x, and then I'll get square root of 5 plus 4y squared times x, as x runs from y up to 2, and then I'm going to let that run from 0 to 2 with respect to y. All right, so I'm just going to induce a 2 minus y on the outside of this. And this is a job for the calculator. Okay, so I'm going to bring that out. I'm going to put it here and call for an integral from 0 up to 2 of 2 minus y. Oh, I'm in polar mode. That's not the place to be. Oh, goodness. 2 minus, I thought I threw in a parenthesis there. 2 minus x times the square root of 5 plus 4x to the 2 dx. what did it think? 5.440 or 5.439. How do we get? That's going to be our surface area. Okay. The last one is, oh, right, but don't evaluate. Okay. An integral expression that gives the area of z equals e to the xy. It sits over the region where x is between 0 and 4 and y is between 0 and 10. Right. And I'm going to get my partial derivatives, set up my integral, and then walk away. Right? So it's going to be the double integral over r of, well, maybe I should write out my partials. Okay, so e to the thing is its own derivative, and then I have to multiply by the derivative of xy with respect to x, so it's like it would be like 5x, and the derivative of that would be 5, so that's why I have the y in front. Then zy equals x e to the xy, and I'm ready to go. So it's going to be the over r of the square root of this thing squared plus that thing squared. Man, that +1 is just killer, right? Because if it wasn't, then I could go to polar probably. I mean, well, that region would be a little annoying, but you know, this is the type of thing you could factor out the e to the 2xy, x squared plus y squared, that's r squared. Oh, but yeah, I wanted to take the square root of that in rectangular. Yeah, this is just like close, but not it. Okay, but this is not as good of a double integral as I could write, right? I could say, I could put these bounds in as well. So that would be as x runs from 0 to 4 and y goes from 0 to 10. You could do it the opposite order. You just need the opposite order of dx and dy over here. Square root of y squared e to the 2xy plus x squared e to the 2xy plus 1. dy and then dx. And that's all I got for you. That was a good collection of surface area problems. Had a nice variety to them. And yeah, I think if you've done this, then you've done enough practice on surface area. So thanks for watching.